Okay, the last video we were working with change in coins and how many different combinations of coins can we have with a given set of denominations for a given amount. This algorithm is called change making problem. So it has the word making in it. So this is where you're actually giving somebody change for a certain amount using a minimum number of coins of denominations. So for example, let's say you go to the store and you give them $1 for a pack of gum that costs 75 cents. And they have to give you change, 25 cents. So you hope that they don't give you all pennies, right? 25 pennies, that would be pretty ridiculous. So we kind of do this naturally in that we always are going to try to give the largest denominations of coins that we can for the change we're given. Or in other words, the minimum number of coins we can possibly give in order to make change. That's what this problem is. So our coin denominations will be listed out as a set like D1, D2, up through DM. So M is going to be our number. M is our number of coin denominations. And N is our amount of change that we need to return to a person. Okay, so chapter 9, which we haven't gotten to yet, so that's the next chapter. It has a greedy algorithm technique to solve this problem, but there's also this dynamic programming technique algorithm, which is why it's in this chapter as well. So in this problem, we're also going to make an assumption that there's an unlimited quantity of coins for each of the denominations. Like we're not going to run out of any of these denominations. We're not going to run out of change. Okay, so since this is a dynamic programming algorithm, that means we're going to be taking up more space in order to save time in our algorithm. And so I want to go through a real example of, let's say our input is going to be an amount of 6. So if it's easier for you to think about this as being dollars instead of coins, since we don't have some of these coin denominations I'm going to be talking about, you can do that. But then we have coin denominations. So our set of coin denominations, which is usually given as an array, is going to be 1, 3, 4. Okay, and our amount is 6. So we need to give change in amount 6 using only these denominations, and we want to give the largest coin denominations possible to do this change. So step 1 is going to be to create an array or a table of size n plus 1. Remember, n is our amount, so 7 elements. Let's see, I want to make this table look pretty. So 1, 2, 3, 4, 5, 6, 7. There we go. 1, 2, 3, 4, 5, 6, 7. And I'm going to go ahead and put the index numbers up above each array element. 4, 5, 6. Yes, that's right. Okay. And I'm going to call this array F. Okay, so I'm going to also have an index value, which I'm going to call I, and set I equal to 0 to begin with. And we're going to initialize f of I. So f of 0 is going to be equal to, is going to be equal to 0. So we're starting this first array element set to 0. All right, now we're ready for the repetitive part. So what we're going to repeat is f of I because we're going to be filling out this table, is equal to the minimum of f of I minus 1 or f of I minus 3 or f of, I need to make this smaller, there we go, I minus 4. And then we add 1 to that, to whichever the minimum is. Now, here's the thing. When I is equal to 0, then we don't want to include any of these array elements for which the coin is greater than 0. So that's what these values stand for. So let's say 1, I'm going to color code this. So 1 is going to be purple from now on. And 3 is going to be, accidentally erased that. 3 is going to be green. So these are representing our coin denominations. And 4 is, let's just make that orange. Okay, so when I is 0, then we're not going to try to find the minimum between any of these at coin 1, 3, or 4 because all of these are greater than 0. So we're going to go ahead and increment I to 1. So I is now equal to 1. So f of 1, f of 1 is going to be equal to the minimum of f of I minus 1. We're going to keep that because 1 is not larger than I, which is 1. 1 is not larger than 1. But we're going to ignore f of I minus 3 and we're going to ignore f of I minus 4 because 3 and 4 are both larger than 1. So minimum of this one value is just going to be this one value. So what is f of I minus 1? It's f of 1 minus 1, so f of 0 is 0. So the minimum between 0 and nothing is going to be 0 plus 1, so that's going to be equal to 1. So f of 1 is 1. Now we're going to increment I. So I is going to be 2. Remember, I is referring to the index value in the table that we're trying to fill out. So f of 2 is going to be equal to minimum of, and we can include the 1, the coin 1, because 1 is smaller than 2. We can't include coin 3 because 3 is larger, or 4, 4 is larger. So f of 2 minus 1 is 1. F of 1 was 1. Minimum between 1 and nothing is going to be 1. We add the 1 to it, so it's going to be 2. So f of 2 is equal to 2. All right, now we increment I again. I is 3. And f of 3 is equal to, I'm erasing all my lines here, is equal to f of 3 minus 1. And we're going to include this one because 1 is smaller than 3. So 3 minus 1 is 2. F of 2 is 2, comma. This time we are going to include this second one for the coin denomination 3 because 3 is not larger than 3. So 3 minus 3 is 0. F of 0 is 0. And we are not going to look at coin 4 because 4 is larger than 3. So the minimum between 2 and 0 is 0. And we're going to add 1 to that, so it's just going to be 1. Okay, now increment I. I is now 4. When I is 4, we're going to include all coins when we're trying to find the minimum. So 4, 3, and 1 are all smaller than or equal to 4, so that will work. We're going to look at all three. Minimum of 4 minus 1 is, let's see, 4 minus 1 is 3. F of 3 is 1. 4 minus 3 is 1. F of 1 is 1. And 4 minus 4 is 0. F of 0 is 0. The minimum of 1, 1, and 0 is 0. We add 1, it's going to be 1. Increment I is now 5. Whoops. There we go. F of 5 is equal to minimum of these three. So 5 minus 1 is 4. F of 4 was 1. 5 minus 3 is 2. F of 2 is 2. 5 minus 4 is 1. F of 1 is 1. The minimum between 1, 2, and 1 is 1. Add 1 to it, that's going to be 2. So F of 5 is 2. Increment I. And when do we stop this algorithm? We stop when I is larger than 6. So right now it's 6, so we're going to keep going. So F of 6 is equal to the minimum between 6 minus 1 is 5. F of 5 is 2. 6 minus 3 is 3. F of 3 is 1. 6 minus 4 is 2. F of 2 is 2. Minimum between 2, 1, and 2 is 1. 1 plus 1 is 2. Increment I is now 7. 7 is larger than the amount, which is 6, so this is where we would stop. Now, how do we know what the answer is? So this is where the answer is in, just like in the last algorithm, is in this very last element in our table, which is 2. So what does 2 mean? That indicates this is how many coins we will, whoops. Oh, that's interesting. I think my application just closed out for no reason whatsoever. Okay, here we are. Okay, so how many coins will be given as change? So that is our output for this algorithm, but that doesn't tell us what the actual coins are. You can, however, figure that out by looking back at which one of the three gave you the minimum, which in our case was this coin with 3, coin 3. So that means we're going to give 2 coin 3s as change. Okay, so that's how you would go through this change making algorithm using the dynamic programming technique. Okay, and I think I do have a practice exercise that I'd like you to try. Let me fast forward through the slides here. Here we are, in class practice. Okay, so this is what you're going to do, and I would like for you to do it before our class on Wednesday morning. So give change for amount 10 using the minimum number of coins of denominations 1, 4, 5, and 6. You may assume that there's an unlimited quantity of coins for each of the 4 denominations. Then I would also like you to try to determine how many coins and also which coins will be used to make the change. So the how many part is easy, and then figuring out which coins would be used just a little bit harder. Here is the pseudocode for this algorithm, and this comes from your book. So it says applies dynamic programming to find the minimum number of coins of denominations. D1 is less than D2 is less than ... less than DM, where D1 is equal 1, that add up to a given amount n. The input is a positive integer n, that's our amount that we're trying to give change for, and an array, this is our coin denomination array, 1 through m, of increasing positive integers indicating the coin denominations. The output is the minimum number of coins that add up to n. So the reason why I called my table, my array that I created F, is because the pseudocode did, and I thought that would make this more clear. But we initialize the very first element in this table to 0. Then we have an outer for loop for I is equal to 1 to n, and I used I as well when I was going through this algorithm. We also have a temporary variable which begins at infinity, and j, another temporary variable, set to 1. So while j is less than or equal to m, remember m is the number of coin denominations, and I is greater than or equal to d sub j, where this is the actual coin denomination we're currently looking at, then this is where we're going to find the minimum between f of I minus that coin, that particular coin denomination, and temp. And so temp begins at infinity, so the first time it's definitely going to be this very first value that gets placed inside a temp. Then we increment j. So this is where the while loop is what allows us to only include the array elements for which the coin denomination is smaller than what I is. And then after this while loop, we will have had the minimum value inside of temp, and so we place temp plus 1 into our array, our table. And our output is f of n, so that is our solution, which indicates how many coins we're going to give as change. Our time analysis and space analysis of the change-making dynamic programming algorithm. So time efficiency is big O of m times n, where m is the number of denominations and n is the amount. And space efficiency is big theta of n, because we had to create one additional array to make this algorithm work.